the previous lecture we were discussing about the continuity equation and how it can be derived from control mass and control volume consideration. Now we have very interesting education system where, I mean, you know, it is very difficult to impress upon the students with a certain form of an equation based on a particular terminology. So I have seen many students whom if you just ask that what is continuity equation, not the physical meaning but the mathematical form, they will not tell the one which I talked about, but they will simply say A1 V1 equal to A2 V2. So this is like a magic simple form of the continuity equation that most of the students are so happy to talk about. So what is that A1 V1 equal to A2 V2? What are the meanings of those notations and how that relates to this continuity equation, that the form that we have discussed, that we will bring out now. So in a way that is about discussing an integral form of the continuity equation. So let us say that we have an arbitrary volume like this, absolutely arbitrary volume, but I mean these are blocked. So fluid enters along x here and fluid leaves along x here. So it is a unidirectional flow, that much we can say. Inside the flow may be 2-dimensional, 3-dimensional, whatever, but from the inlet and the outlet perspective they are unidirectional flows. So now we assume that it is a steady flow. This is the first assumption. And a very important assumption. Then we are left with now let us integrate this equation over the volume of this, because the equation itself right hand side equal to 0, its integral is also 0. So now what we will do is we will use the divergence theorem. So using the divergence theorem we will convert this volume integral into an area integral. So this will be where A is a closed area that that is surrounding the volume V. Okay. With this, now that area has 4 parts: this part, this part, this part and this part. Out of these there is no velocity across these two. So clearly if you call this as area 1, if you call this as area 2, then it is a combination of for area 1. So this is x direction, V is ui because it is unidirectional flow, eta is the unit vector outward normal to this is minus I cap. For area 2 it is ui and this is plus I cap. So you are left with minus integral rho u dA for area 1 plus integral rho u dA for area 2 is equal to 0. Next, let us make an assumption that rho is constant. So up to this, steady flow would have been fine, rho might not be a constant. Here, from here onwards, we are assuming that rho is a constant. If rho is a constant, it gets cancelled from the two sides. So you are left with integral u dA over 1 is equal to integral u dA over 2, right. So by the definition of average velocity, this is u1 average into a1 and the right hand side is u2 average into a2. So this is the so called a1 v1 equal to a2 v2. So remember that this v1 or u1 average, whatever you call, this is average velocity at section 1, not velocity at point 1, because many students with a misunderstanding write this, interpret this as velocity at point 1. No, this is average velocity at section 1 and this is average velocity at section 2. The beauty of this is that it is just good enough to have unidirectional flow at these two sections. Inside you may have whatever 2-dimensional, 3-dimensional flow, it does not matter. And in fact, in such a geometry you will definitely have at least a 2-dimensional flow inside. Why? Because the area of cross section is changing, the x component of velocity will also change to satisfy the mass flow. So u is a function of x. Because u is a function of x, you must have v also a function of y, because del u del x plus del v del y equal to 0 for the continuity equation to be satisfied. So with u and v both components present, you will have a 2-dimensional flow structure. So inside the flow is not unidirectional. Still this simple formula works. So the only restriction is that unidirectional flow at inlet and outlet and rho is constant. The final concepts that we will discuss in the context of kinematics of flow will be about two important parametric representations of various kinematic constraints. One is the stream function and another is the velocity potential. So stream function. Let us say that you have a 2-dimensional incompressible flow. So you have del u del x plus del v del y equal to 0. This is, I mean, you may call it related to continuity, but it is also a kinematic constraint. The problem in handling with this equation is that there are two dependent variables u and v, but there it is just a single equation. So it would be very nice if this equation is expressed in a parametric form. So in that way you define if you define this, then you can clearly see that this parametric definition where psi is a function of x and y will satisfy this equation automatically. Okay. So this psi is called as stream function. Now the question is, we will address two important points here which are points normally raised by the student. One is, what is the sanctity of this plus and this as minus? There is absolutely no sanctity, they have to be just opposite sign to satisfy this equation. So one convention could be this, another convention could be this as minus and this as plus. The other question that comes to the minds of the student is that why out of so many names, possible names, the name of stream function, and that can be answered in a very simple way. So if you calculate, so this okay. So when you have d psi equal to 0, then you have dx by u is equal to dy by v. This is nothing but equation of a streamline. So stream function is constant because d psi is 0, that means psi is equal to constant. Stream function is constant along a streamline. Okay. Now this again creates a confusion in the mind of a student. So that means the student interprets it in a little bit of convoluted way, that a streamline always means a constant stream function line. This is not true, because streamlines are defined also for 3-dimensional flow or also for compressible flow, but stream function is defined only for 2-dimensional incompressible flow. So although streamlines may exist, but that may not represent a constant stream function. So this relationship between stream function and streamline is there only when both are simultaneously defined. Okay. So far so good. We will now consider another limit of the rotationality, that is the irrotational flow. So if you have irrotational flow, you have by a vector identity, this is identically a null vector, this is a vector identity. Therefore for irrotational flow, only for irrotational flow, you can write okay. So this phi is called as velocity potential. So in field theory, a field can be expressed as a gradient of a scalar potential if it is a conservative field, and in an irrotational flow, if there is no viscosity or no viscous effect, rather the flow field will remain conservative, that means there will be no viscous dissipation, and that is why this can be expressed as the gradient of a scalar potential. So now we have two interesting definitions, one is inviscid flow, one is incompressible flow, another is irrotational flow. Now based on these two, we have defined two parameters phi and psi. How are they related? So let us define a case which is a special case, 2-dimensional plus incompressible plus irrotational flow. This special example is to represent a situation when phi and psi are both defined. So you can make a comparison. So if you have psi equal to constant line, you can write d psi equal to 0, so this is u and v. So, dy dx for psi equal to constant is equal to v by u. Similarly, phi equal to constant line, so this is u and this is v. Okay. So, dy dx for psi equal to constant times dy dx for phi equal to constant is equal to v by u into minus u by v, right. There is a temptation of cancelling these, but we are not always in a position to do that if u and v are 0. So, there is a special point where definitely we cannot cancel this, and that point is where both u and v are 0. That special point in the flow field is called as stagnation point. From the English word stagnation, you can understand that that means the flow is stagnated, that means its velocity is 0. So, at stagnation point you do not have a defined calculation for this, but if u and v are either not equal to 0, then you can simply cancel it. If it is minus 1, then it becomes minus 1, provided u v are not equal to 0. Okay. So, that means this is the slope of the tangent to the psi equal to constant line, this is the slope of the tangent to the phi equal to constant line, and the product of that is minus 1, that means their tangents are perpendicular to each other. These are called as orthogonal curves. So, you have say phi equal to constant and so they are orthogonal to each other, means if you draw tangent at a common point, then the angle between them is 90 degree. So, in computational fluid mechanics you can generate grid lines using these, and they will, these phi equal to constant lines and psi equal to constant lines form nice orthogonal set of grids, and these lines are all, this kind of network structure that these grids form is also called as a flow net. So, that is again a very important definition in the context of this. Finally, what are the governing equations that phi and psi satisfy in this? So, let us say that you have 2-dimensional plus incompressible flow. So, you have del u del x plus del v del y equal to 0. For this, the definition is u is equal to del psi del y and v is equal to minus del psi del x. So, if it is irrotational flow, in addition remember that this is twice the angular velocity. So, irrotational flow means this is equal to 0. So, this will give you okay. Similarly, if it is irrotational flow from a different angle, u is equal to del phi del x, v is equal to del phi del y. For incompressible flow, okay. So, for 2-dimensional incompressible and irrotational flow, both phi and psi satisfy this template. Which is the Laplace equation in 2D. This is the Laplacian operator in 2D. So, they both of them satisfy the same equation, but interestingly their solutions are orthogonal, and the reason is that their boundary conditions are different, that is why their solutions are orthogonal. So, with this little bit of discussion on the stream function and the velocity potential, we will work out a simple problem, the outline of a simple problem, and then we will call it a day so far as our discussion on kinematics is concerned. So, let us say that you have a velocity field W is not 0, let us say W equal to some B, okay, in appropriate units. So, the question is, number 1, does phi exist, the velocity potential? If so, you derive an expression. Number 2 is calculate, or better to say determine, because it is not a numerical calculation, the projection of a streamline on xy plane. Okay. So, first, how do you assess whether the velocity potential will exist? You just test whether it is irrotational flow. So, here the irrotationality can be tested with just u and v component, because w is just a constant, it does not have any derivative. So, you have so maybe let us just redefine the problem, otherwise, so just put it a into x plus y and this as a into x minus y, otherwise it is not coming as irrotational, so we cannot really, I cannot illustrate you the problem. So, just change this x plus y and x minus y. So, this is a minus a, this is 0. So, that means it is irrotational flow. So, u is equal to del phi del x okay. So, if you integrate this, remember this is called as partial integration. So, integration with respect to x keeping y and z as constant. So, a x square by 2 plus a x y, so this is phi, plus with respect to x when it is integrated, functions of y and z are like constant. So, plus a function of y and z. This is where lots of students make mistake, because they forget the partial integration and they just write this as a constant of integration, which is not correct. Similarly, function of x and z, and w is equal to b. Right. Now, these three are essentially representations of the same function. So, if you compare this, you will get f1 is equal to what? Minus ay square by 2 plus bz. f2 is ax square by 2 plus bz, and f3 is ax square by 2 plus axy minus ay square by 2. So, what is phi? Phi is ax square by 2 plus axy minus ay square by 2 plus bz. You can add a constant, but this constant can be set to 0 by choosing the reference that at x, y, z equal to 0, phi is 0. You can choose an arbitrary reference and then set the value of c. Okay. The second part, I will not go through such detailed calculation, but I will just give you an outline. So, projection of a streamline on the xy plane. See one interesting thing. What is del u del x? It is a. What is del v del y? That is minus a. So, what is del u del x plus del v del y? This is 0, but it is actually a 3-dimensional flow. So, for 2-dimensional incompressible flow, del u del x plus del v del y equal to 0, but if del u del x plus del v del y equal to 0, it may not necessarily be a 2-dimensional flow. This is just a example, but once it is satisfied, the definition of stream function is dependent on this equation's parametric form. So, once this equation is satisfied, you can definitely write u equal to del psi del y and v is equal to minus del psi del x, and then write this as a into x plus y, write this as a into x minus y. Just in the same manner as we did for phi, you can partially integrate and get the psi equal to constant, which in this case is a projection of the streamline on the xy plane. So, we have come to the end of our discussion on kinematics of flow. We have essentially discussed about the flow description through Eulerian and Lagrangian description, different types of flow, description of velocity and acceleration using Eulerian variables, and subsequently discussions on streamline, streak line, path line, that is the flow visualization lines, and detailed discussion on deformation, linear, volumetric, angular, and then bringing the perspective of continuity equation through the volumetric deformation, and eventually parameterizing the condition for 2-dimensional incompressible flow and the general irrotational flow through the parametric representations in terms of stream function and velocity potential. So, these are I think the essential contents of fluid kinematics, no matter
what is the level of the course that you are talking about. These are the essential contents that need to be covered. With this we stop here today, and in the next set of lectures we will start with the dynamics of flow, and first we will be talking about the dynamics of flows where viscous effects are not important. Thank you very much.